My name's Tom Dick. I'm a math professor and math advisor for Texas Instruments. And this short video is part of the TI-Nfocus AP Calculus series. We're going to take a look at analyzing functions from tables of data using a context from BC Calculus on a problem patterned after the 2020 AP exams. Let's take a look. So our context is particle motion in the plane. So the position of the particles given by x of t comma y of t. T is measured in seconds. X of t and y of t are twice differentiable functions, and they're measured in meters. We've got an explicit formula for x prime of t, but we only have selected values of y prime of t in a table over the time interval 0 to 12. We're also given that the position of the particle at time t equal 12 is 4, negative 3. Now on this page, we've got a list in spreadsheets, and we've entered our table of values. So I've got a column labeled time. These are the time values. And we also have a column labeled YDER for y derivative. So these are our y prime values. And these are the only values we know for y prime. All right, we're going to use Euler's method to approximate the y-coordinate of the particle at time t equal 4. Now notice time t equal 4 is not in our table. So we're going to insert a row for that time. Okay, so we've got an inserted row, and I'm going to enter 4 for the time. And I'm going to leave y dir blank because we don't know what y prime is at that time. But we do want to approximate what's the y-coordinate of the particle at that time. I'm going to put in yp for the y position, and I'm going to name this next column delta y. So this is kind of our workspace for doing Euler's method in a spreadsheet. Let me widen that column out just a little bit. There we go. Now the time that we have a position given for us, y-coordinate, is at t equal 12. And we know that the y-coordinate at that time is negative 3. So that's where we're going to work from. So now we're going to work backwards. We'll go from time t equal 12 to t equal 10. We know the derivative of y is negative 5. And we're going to step back negative 2. And we get an increment of 10. Negative 5 times negative 2. So I'm going to add that 10 to the negative 3 we started with, and notice I just used a spreadsheet, made that equal to C7 plus D7, and that gave us our negative 3 plus 10 is 7. And now we'll just do this again. Now that we're at time t equal 10, the derivative there is negative 1 times our step size of negative 2 is a positive 2. We'll add that to the 7, so I'm going to add C6 and D6, the 7 plus the 2. And that gives us our position estimate at time t equal 8. At time t equal 8, our derivative is 3. So we'll multiply 3 times our step size of negative 2 to get our delta y. We'll add that to our previous position of 9. So I'm adding C5 and D5. 9 plus negative 6 is 3. And we've got one more step to take to get to t equal 4. So our derivative at t equals 6 is negative 2 times our step size of negative 2. That gives us 4. And then we'll add the 3 and the 4. So I'll add C4 and D4. And that's going to give us our Euler's method approximation for the y-coordinate at t equal 4, which is 7. With Euler's method, we actually have approximations of positions for the times between t equal 12 and t equal 4. Let's go ahead and compute the x-coordinate positions at those same times, except now we'll be able to do those exactly. On the next page, you'll see that I've defined something called x del of t, and that gives us our change in the x-coordinate from time t equal 12 to any time t. We're going to use that to generate the x-coordinates for those same times that Euler's method gave us approximations for y-coordinates. So I'm going to label this xp for x position, and it'll be defined as, let's see, our position at time t equal 12 was 4, so I'm going to make this equal to 4 plus our change in x position, which is that x del of, well, in this case, the time t is in A1. And there's our position, x coordinate of our position at time t equals 0 is -4. Now we're just going to fill down using this spreadsheet functionality, and we get all the x positions at the times that are in the table. Now that we have both x positions and y positions for times t equal 4, 6, 8, 10, and 12, what I'd like to do is actually do a scatter plot of the positions, and here it is. So please keep in mind that our x and y coordinate functions were twice differentiable, so the path of our particle should appear pretty smooth. What I've done here is just connect up some selected positions with straight line segments. And also keep in mind that we only had approximations for the y coordinates because we used Euler's method. The x coordinates are all exact. Well, that winds up this short video. For more resources like these, please see education.ti.com.